Imagine watching a weather anchor, just casually dodging a massive 3D rendered hurricane right in the middle of the studio.
Yeah, it is pretty wild to watch.
Right. And to make that illusion hold up without the digital graphics just sliding all over the screen, you actually need a camera that speaks directly to the virtual world. So today, we are doing a deep dive into the spec sheet of the $4,895 Bolin Technology R9-230NXW PTZ, or a pan-tilt zoom camera.
From HDTVSupply, yeah.
Exactly. We want to decode this dense technical document to see exactly how it bridges physical and digital reality.
Because hidden inside these specs is basically the exact blueprint for how modern live sports, news broadcasts, and even VR productions actually pull off those illusions. I mean, the hardware listed here is doing some incredibly heavy lifting.
Okay, let's unpack this. Because before a camera can start creating virtual worlds, it has to flawlessly capture the physical one, right? Even in terrible lighting. It's like crossing a wildlife tracker's binoculars with full-color night vision.
That is a great way to put it, honestly. Looking at the core hardware on this Bolin camera, it pairs high-quality optical glass with an 8-megapixel sensor. Specifically, it is a Sony 11.8-inch Storvis stress sensor.
Okay, wait, 11.8-inch, is that big for a camera like this?
Yeah, that physical size is crucial here. A 11.8-inch sensor is larger than what you typically find in standard broadcast gear. So its individual pixels act like bigger buckets, catching more light.
Ah, so that is why its color holds up so cleanly in the dark.
Exactly. But, pulling in all that ambient light is really only half the battle. It also features a massive 30x optical zoom.
Right, and if you have ever tried to hold a pair of binoculars steady at 30x magnification, even a simple heartbeat makes the image bounce around. So how is the super image stabilizer listed in these specs actually compensating for movement? I mean, without a human operator physically holding it steady.
Well, instead of just digitally cropping the image, which obviously degrades the resolution, this system physically shifts the optical glass elements inside the lens barrel in real time.
Wait, a glass itself is moving?
Yep. It uses internal gyroscopic sensors to detect tiny vibrations. So if a heavy camera crane sways or, say, a stadium floor vibrates from a cheering crowd, the gyroscope detects that motion.
Oh, wow.
Yeah, and then it moves the lens in the exact opposite direction to basically cancel it out.
So it can lock on to a running player in a dimly lit stadium at 30x zoom. That is wild. But a flawlessly sharp image is useless to a modern broadcast if the digital graphics layered on top of it are sliding all over the place.
Which they absolutely will do if the tracking is off.
Right. So how does this camera tell the digital world exactly what its physical lens is doing?
That brings us to the Freed protocol. Freed feeds highly precise real-time axis data, so specifically the exact pan, tilt, and zoom movements, and it sends that directly into broadcasting software over a network.
Here's where it gets really interesting, because anyone who has worked in broadcasting knows the absolute nightmare of matching moving PTZ cameras with dynamic digital environments. Traditionally, you needed static cameras and green screens for this.
Oh, absolutely.
Yeah.
It used to be a very rigid setup.
So I have to push back here. Tracking a camera's physical movement is one thing, but does this freed data mean the camera can actually move around a physical set while keeping those 3D illusions perfectly anchored?
Yes, because the free data tells the software exactly where the physical camera is pointing and how far it is zoomed down to the millisecond. So the software can instantly calculate the exact perspective needed to render the 3D graphics.
But what about latency? If the camera pans even a fraction of a second faster than the CGI renders, the illusion completely breaks. How does Freed handle that kind of continuous data stream without lagging?
It manages it by keeping the data packet incredibly lightweight. Freed isn't sending heavy video files to the virtual environment at all. It is just sending a tiny string of hexadecimal code over a standard IP network.
Just code.
Right, that string essentially just says X position, Y position, Z position, zoom mount, focus mount. Because the data footprint is so small, it can update 60 times a second, perfectly in sync with the video frames.
So the virtual world moves flawlessly right along with the physical camera sweep. That is fascinating. So what does this all mean?
What we're looking at tools that perfectly align physical reality with digital rendering, instantly and without human intervention.
Exactly. For you listening, it means the next time you see a live sports broadcast painting real-time player stats directly onto a moving football field, or a studio set expanding into a vast virtual stadium, you are watching the Freed protocol and automated PTZ cameras in action.
Yeah, this technology is essentially tying an invisible mathematical thread between a piece of moving optical glass and a server rendering a virtual environment.
Which leaves you with this to chew on. If automated robotic cameras can flawlessly track human movement while rendering real-time virtual environments around them, how long until the line between a physical live broadcast and a fully rendered digital simulation vanishes entirely?